Here's something that should keep you up at night, but probably won't. What if there was a place in the universe where time itself slowed to a crawl, then stopped? A place where gravity became so overwhelmingly powerful that nothing, not even light, could escape its grasp once it passed a certain boundary. A place where the very fabric of space and time was stretched and twisted into a shape so extreme that our most fundamental laws of physics simply give up. This isn't science fiction, though it sounds like it. This is the reality of a black hole. Think about that for a moment. Light, the fastest thing we know, travelling at nearly 300,000 kilometers per second, a speed so immense that a beam could circle the Earth over 7 times in a single second, yet within a black hole light is trapped permanently. It's like being caught in an infinitely deep well, where no matter how fast you climb, the sides are always pulling you down harder, faster, until escape becomes utterly impossible. And this isn't just about light. It's about anything. Planets, stars, dust, gas, even the most fundamental particles of reality. Once they cross an invisible line, they are gone forever, swallowed into an abyss from which no information, no signal, no whisper can ever return to the outside universe. The fascinating thing about black holes is not just their immense destructive power, but what they represent: extreme laboratories of the universe. They are places where our understanding of gravity, space, and time is pushed to its absolute limits, revealing where our current physics models break down and hinting at the deeper, more unified theories that we are still searching for. They are cosmic paradoxes, simultaneously the simplest objects in the universe, described by just 3 numbers: mass, spin, and charge, and yet the most mysterious holding secrets that could redefine our understanding of existence itself. If you're enjoying this journey through science, hit that like button and subscribe so you don't miss future episodes. And I'm always curious. Drop a comment, letting me know what city and time zone you're watching from. There's something special about knowing this story is reaching people all over the world. Now, let's begin our descent into the cosmic abyss. Here's a thought experiment to begin our journey. Imagine throwing a ball straight up into the air. What happens? It goes up, slows down, and eventually falls back to Earth. But what if you could throw it incredibly fast? Fast enough to break free from Earth's gravity entirely and fly off into space, never to return. That minimum speed is called the escape velocity. For Earth, it's about 11.2 kilometers per second, or roughly 25,000 miles per hour. That's a truly immense speed, but it's achievable. Rockets do it all the time. Now here's where it gets mind-bending. What if something was so incredibly massive and so incredibly compact that its escape velocity was greater than the speed of light itself? That, my friends, is the fundamental, mind-numbingly simple definition of a black hole. Let's start with the familiar. Everyone knows gravity. It's the force that pulls the apple from the tree, keeps our feet on the ground, and holds the planets in orbit around the sun. For centuries, our understanding of gravity was largely shaped by Isaac Newton's brilliant insights. Newton described gravity as an invisible force acting between any 2 objects with mass. The more massive the objects, the stronger the pull. The closer they are, the stronger the pull. This is elegantly captured in his law of universal gravitation, which tells us that the force of gravity is proportional to the product of their masses and inversely proportional to the square of the distance between their centres. This inverse square law means that if you double the distance between 2 objects, the gravitational force between them drops to a quarter of what it was. It's a beautifully simple, incredibly powerful mathematical description that allowed us to predict the orbits of planets and even discover new ones. Building on Newton's ideas, in the late 18th century, 2 independent thinkers, John Michel in England and Pierre-Simon Laplace in France, speculated about dark stars. They reasoned that if a star were massive enough and condensed into a small enough volume, its gravitational pull could become so intense that its escape velocity would exceed the speed of light. Since light was then believed to be made of particles, corpuscles, and those particles had mass, they argued that even light itself would be trapped, unable to escape the star's surface. These dark stars would be invisible, their presence only detectable by the gravitational influence they exerted on other celestial bodies. This was an astonishingly prescient idea, conceived long before Einstein, and it already contained the core concept of the black hole, a region of space from which nothing, not even light, can escape. The reason this concept matters so profoundly is that it introduces us to the idea of a physical boundary, a point of no return. For Earth, if you launch a rocket at less than 11.2 km, it eventually falls back. At exactly 11.2 km, it escapes with zero speed, just barely making it out. Above that, it escapes with some residual speed. But what if the speed limit of the universe, the speed of light, which is approximately 299,792,458 meters per second, became the escape velocity for an object? That object would be an ultimate gravitational trap, and that boundary is precisely what we call the event horizon. Now, while Michel and Laplace were remarkably insightful, their understanding of gravity was based on Newton's framework, which viewed gravity as a force. It wasn't until Albert Einstein came along with his general theory of relativity in 2015 that we truly began to understand the profound nature of gravity, and therefore of black holes. For Einstein, gravity isn't a force pulling objects together. Instead, it's a manifestation of the curvature of space-time itself. Imagine space-time as a colossal, invisible, flexible fabric. Massive objects like stars and planets don't just sit on this fabric, they dent it. They warp it. And what we perceive as gravity is simply objects following the curves and contours created by these dents. This might sound abstract, but it's a critical shift in understanding that helps us grasp the true nature of a black hole. So let's return to the event horizon. In Einstein's view, the event horizon isn't just where the escape velocity exceeds the speed of light. It's where the warping of space-time becomes so extreme that all paths, all directions, all future possibilities lead inward. It's not a physical surface you'd crash into. You wouldn't even necessarily feel yourself crossing it. Instead, it's a boundary in space-time itself, a point beyond which the very structure of the universe dictates that every trajectory, including that of light, must move towards the central singularity. Think of it like a river flowing faster and faster. If you're in a boat trying to paddle upstream, you might be able to make progress for a while, but eventually you'll reach a point where the current is moving faster than you can paddle. Once you cross that invisible line, no matter how hard you paddle, you're carried downstream with no possibility of turning back. The event horizon is precisely that point, but for space-time itself, and the current is the relentless pull towards the black hole's center. To appreciate the extreme density required to form such an object, consider this. If you wanted to turn our own Earth into a black hole, you'd have to compress its entire mass into a sphere about the size of a marble. The Sun, far more massive, would need to be squeezed down to a radius of approximately 3 kilometers, roughly the size of a small city. This is why black holes are such exotic objects. They represent the ultimate triumph of gravity, where matter has been crushed to densities that defy our everyday intuition. We can't see them directly because no light escapes, but we infer their existence from their powerful gravitational effects on surrounding matter, such as the swirling superheated gas of an accretion disk, or the extreme orbits of stars around an unseen central mass. The implications of this point of no return are staggering. Everything that crosses the event horizon is gone, forever. From the perspective of an outside observer, any information about the object, its composition, its shape, its history, seems to vanish. This leads to what's known as the no-hair theorem, a fascinating concept that states that once an object falls into a black hole, the black hole itself can only be characterized by three intrinsic properties: its mass, its angular momentum or spin, and its electric charge. All other details, all the hair of the object, are effectively smoothed away. It's like dropping a dictionary into a black hole. The black hole doesn't get smarter or know more words, it just gets a tiny bit more massive. This apparent loss of information has profound consequences for our understanding of the universe, hinting at a deep conflict between general relativity and quantum mechanics, a conflict we'll explore in much greater detail later in our journey. For now, understand that the event horizon isn't just a boundary, it's a cosmic veil behind which the rules of our familiar universe begin to fray. So we've established the black hole as a region where light and everything else can't escape due to the most extreme form of gravity imaginable, defined by the event horizon. But saying gravity is strong isn't enough to truly grasp what's happening. We need to understand what gravity actually is at this extreme beyond Newton's familiar force. This leads us to Einstein's revolutionary insight. Gravity isn't just a force, it's a manifestation of the curvature of space-time itself. In our next chapter, we'll dive into the elegant and mind-bending world of general relativity and see how this new understanding of gravity fundamentally reshapes our view of the universe and, crucially, of black holes, setting the stage for our eventual journey across the event horizon. In Chapter 1, we grappled with the profound mystery of the no-hair theorem, a cosmic barber's cut that seems to strip away all the unique characteristics of matter once it falls into a black hole, leaving only its mass, spin, and charge. This apparent loss of information, as we discussed, isn't just a quirky detail, it represents a fundamental clash between two of our most successful theories, Einstein's general relativity and the bewildering world of quantum mechanics. It's a puzzle that continues to vex the brightest minds in physics. But before we dive deeper into that paradox, let's take a closer look at the boundary itself, the event horizon, and what it truly means to approach and perhaps cross it. Imagine, if you will, that we're embarking on this journey together, not as mere observers from a safe distance, but as intrepid explorers drawn inexorably towards one of these cosmic behemoths. What would we truly see and feel as we hurtle towards that point of no return? From a safe distance, watching an object, let's say a brave, if foolhardy astronaut, fall into a black hole, the first thing we'd notice is something utterly bizarre happening to time. As our astronaut approaches the event horizon, their movements would appear to slow down, as if caught in an invisible molasses-thick current. Their clock, visible through the viewport of their spacecraft, would tick slower and slower relative to ours. Their radio messages, if they could still send them, would drop in pitch and stretch out, eventually becoming an infinitely long, silent hum. This isn't some trick of perception. It's a fundamental consequence of general relativity known as gravitational time dilation. The immense gravity of the black hole warps space-time so severely that it literally stretches time itself. From our vantage point outside, the astronaut would never quite reach the event horizon. They would appear to freeze, eternally suspended just inches from the edge, their image fading and reddening as the light they emit struggles to escape the black hole's tightening grip, losing energy along the way. It's as if the black hole casts a spell, freezing time for anyone who dares to approach its precipice, transforming them into an eternal ghostly silhouette against the cosmic backdrop. This is the edge of forever for an outside observer, a truly mind-bending concept. But what about our brave astronaut? What do they experience? This is where the narrative shifts, and the true terror and wonder of a black hole truly unfold. As the astronaut crosses the event horizon, they wouldn't necessarily feel anything dramatic at that precise instant. There's no physical barrier, no cosmic tripwire. For them, time would continue to flow normally. Their own clock would tick at its usual rate, and their heart would beat with the same frantic rhythm. The outside universe, however, would begin to accelerate dramatically from their perspective, perhaps flashing by in a blur of light and stretched out colours as all the future of the cosmos plays out in an instant behind them. Once inside the event horizon, the rules of the game change entirely. Imagine space-time not as a static backdrop, but as a flexible fabric, as Einstein taught us. Now imagine that fabric being dragged inward, like water rushing down a drain, faster and faster. Inside the event horizon, this inward flow of space-time exceeds the speed of light. Every path, every direction, including the one that seems to lead back out, now points inevitably toward the black hole's center. It's like being in a river whose current is moving faster than you can swim. No matter how hard you paddle upstream, you're still being carried further and further downstream. Inside the event horizon, all upstream paths lead inward. Escape is not just difficult, it's physically impossible. This brings us to one of the most vividly terrifying aspects of falling into a black hole: spaghettification. As our astronaut plunges deeper, they would begin to feel an incredible, unimaginable stretch. This isn't just gravity pulling them down, it's the difference in gravitational pull across their body. The part of their body closer to the black hole, say their feet, would experience a significantly stronger gravitational force than their head. Simultaneously, the gravitational pull from the sides would be weaker, compressing them laterally. The result? Our astronaut would be stretched lengthwise and squeezed widthwise, like a piece of spaghetti being pulled and thinned. Think of it this way. Earth's gravity pulls on your head and your feet with almost the same force because you're relatively small compared to the Earth's radius. But near a black hole, the gravitational field changes so rapidly over short distances that the difference becomes immense. For a typical stellar mass black hole, one formed from the collapse of a star, these tidal forces would become lethal long before you even reach the event horizon. You would be torn apart atom by atom into a stream of subatomic particles long before you could truly ponder your fate. A rather messy end, wouldn't you agree? However, there's a fascinating caveat. For truly supermassive black holes, the kind found at the centres of galaxies, like Sagittarius A in our own Milky Way, the event horizon is much, much larger. Because the black hole is so vast, the gradient of gravity across a human body at the event horizon is actually much gentler. In theory, you could cross the event horizon of a supermassive black hole without immediately being spaghettified. You might not even notice the moment you crossed, apart from the sudden, chilling realization that you are now irrevocably committed to an inward trajectory. But even with a gentle crossing, your fate is sealed. Once inside, the relentless march toward the center accelerates. The tidal forces, though initially mild for a supermassive black hole, would continue to grow exponentially as you approach the ultimate destination, the singularity. The singularity is where general relativity, in its current form, throws up its hands and admits defeat. It's the theoretical point, or perhaps a ring for a spinning black hole, where all the mass of the black hole is compressed into an infinitely small volume, resulting in infinite density and infinite space-time curvature. At this point, the very fabric of space-time is stretched, twisted, and torn beyond all recognition. Our familiar laws of physics, the equations that govern everything from the falling of an apple to the orbits of galaxies, simply cease to apply. They break down. They give us infinities, which in physics usually means our theory is incomplete or has reached its limits. Imagine trying to describe the temperature of ice using only equations designed for fire. It simply doesn't work. The singularity represents a boundary not just in space and time, but in our understanding of reality itself. What happens at the singularity? We don't know. Does space-time continue beyond it? Is there a bounce, a new universe? These are questions that push the very edge of our scientific and philosophical inquiry. This is precisely why black holes are such crucial laboratories for theoretical physicists. They are extreme environments where the universe forces us to confront the limitations of our current theories. The breakdown of physics at the singularity is one of the most compelling reasons we desperately need a unified theory of quantum gravity. A theory that can reconcile Einstein's macroscopic view of gravity with the microscopic, probabilistic world of quantum mechanics. It's hoped that such a theory would provide a coherent description of space-time and matter under these extreme conditions, perhaps revealing what truly lies at the heart of a black hole, and offering an answer to the terrifying infinities of the singularity. And what about that information paradox we touched upon at the end of Chapter 1? If all matter is crushed into a singularity, and all its unique hair is seemingly lost, where does the information go? Quantum mechanics insists that information can never truly be destroyed, only transformed. Yet, general relativity, in its pure form, suggests that anything falling into a black hole is gone forever, its information seemingly wiped from existence. This fundamental disagreement is one of the most profound challenges facing modern physics. Does the information reside somewhere within the distorted space-time? Does it somehow escape through a mechanism we don't yet understand, perhaps related to Hawking radiation? Or is our understanding of either quantum mechanics or gravity, or both, fundamentally flawed at these extreme boundaries? The journey into a black hole, then, is not just a physical descent into an abyss of gravity. It's a descent into the deepest mysteries of the universe. It's a place where time and space lose their familiar meaning, where matter is unmade, and where the very laws of physics, as we know them, unravel. We've only just begun to scratch the surface of these cosmic enigmas, and the deeper we go, the more profound the questions become. In our next chapter, we'll begin to explore some of the most mind-bending theories proposed to address these paradoxes, from wormholes to the holographic principle, as we continue our quest to understand what truly happens inside a black hole. The singularity, that infinitely dense and infinitely curved point at the heart of every black hole, represents more than just a physical destination. It is a profound intellectual barrier. Here, the elegant equations of Einstein's general relativity, which so beautifully describe the cosmos on grand scales, scream error and dissolve into mathematical nonsense. Infinities erupt, signalling not an infinite truth, but the absolute limit of our current understanding. For us, this breakdown isn't a failure but an invitation. It tells us that to truly grasp what happens inside a black hole, we need new physics, a more complete picture of reality that can reconcile the macroscopic world of gravity with the bizarre probabilistic realm of the very small quantum mechanics. This is where the story truly takes a mind-bending turn, plunging us into one of the most contentious and fascinating debates in modern physics, the black hole information paradox. You see, the no-hair theorem we touched upon earlier, the idea that black holes are defined only by their mass, spin and charge, implies something deeply unsettling. When matter, with all its intricate details and unique quantum information, plunges past the event horizon, it seems to be utterly compressed and smoothed out into these three simple properties. All the unique information about what the matter was, whether it was a star, a planet, a dictionary, or even a single subatomic particle, appears to be lost forever. But here's the rub, and it's a monumental one. Quantum mechanics, the bedrock of our understanding of the universe at its most fundamental level, insists with unwavering certainty that information cannot be destroyed. It can be scrambled, transformed or hidden, but never truly erased from existence. Imagine burning a book. The information isn't gone, it's just incredibly difficult to retrieve, encoded within the smoke, ash and heat. Quantum mechanics states that in principle, if you could precisely measure every particle, you could reconstruct the book. Now, apply this principle to a black hole. If a black hole swallows a book, and all that remains is its increased mass, spin and charge, where did the information about the words, the ink, the paper, the atomic configurations go? If it's truly gone, then a fundamental tenet of quantum mechanics, the conservation of information, is violated. This isn't just a minor disagreement. It's a head-on collision between two of our most successful scientific theories. General relativity says information is destroyed. Quantum mechanics says it must be preserved. This, dear friends, is the information paradox, and it has kept some of the brightest minds awake for decades. For a long time, the prevailing thought was that black holes were cosmic roach motels. Matter checks in, but it never checks out. Information was simply lost. But then, in the 1970s, Stephen Hawking dropped a bombshell that completely redefined our understanding of black holes and intensified the paradox. He proposed that black holes aren't entirely black. They slowly radiate energy and eventually evaporate, a phenomenon now known as Hawking radiation. How does this happen? It's a truly astonishing quantum effect that occurs right at the event horizon. In the vacuum of space, even in seemingly empty regions, quantum mechanics tells us that pairs of virtual particles and antiparticles are constantly popping into existence and annihilating each other almost instantaneously. Think of them as tiny, fleeting energy fluctuations. Most of the time they blink into and out of existence without consequence. But what if one of these virtual pairs appears right at the event horizon? Imagine a particle-antiparticle pair, say an electron and a positron. One of them, perhaps the positron, falls across the event horizon irrevocably trapped, while its partner, the electron, escapes into space. To an outside observer, it looks as if the black hole has emitted a particle. Where does the energy for this escaping particle come from? It's literally drawn from the black hole's own mass. Over immense timescales, this continuous process of emitting particles causes the black hole to slowly shrink, losing mass and eventually evaporating entirely. This is a profound revelation. It means black holes aren't eternal prisons. They have a finite lifespan. A stellar mass black hole might take trillions of years to evaporate, far longer than the current age of the universe. But tiny primordial black holes, if they exist, could evaporate much faster, perhaps even exploding in a final burst of energy. Now, here's where Hawking radiation twists the knife in the information paradox. If a black hole eventually evaporates and all that's left is radiation, what happens to all the information about the matter that fell in? Does it come out encoded in the Hawking radiation, or is it truly gone forever, vanishing with the black hole's final puff? Hawking initially argued that the radiation was purely thermal, meaning it carried no information about the black hole's past contents, much like the steam from a boiling pot of water. Tells you nothing about the specific ingredients that went into the pot. If this were true, then information is indeed destroyed, and quantum mechanics as we know it would need a serious revision. It would imply that the universe is not deterministic in the way we always believed, that history could truly be erased. This prospect sent shivers down the spines of many physicists, notably Leonard Susskind and Kip Thorne, who championed the idea that information must be conserved. The stakes are incredibly high. If information can be destroyed, it undermines the very foundations of quantum theory and throws into question our understanding of causality and the fundamental laws of nature. So where do we stand on this cosmic cliffhanger? The scientific community is largely converging on the idea that information is in fact conserved. Hawking himself later reversed his position, suggesting that information might escape in a scrambled but recoverable form. But how it escapes and how it's encoded in the Hawking radiation remains one of the deepest mysteries. This quest to reconcile gravity and quantum mechanics to solve the information paradox has led physicists down some truly wild and speculative paths, pushing the boundaries of human imagination. We're talking about theories that propose extra dimensions, vibrating strings, and a universe that might be a hologram. One of the leading contenders for a theory of quantum gravity is string theory, and its more encompassing form, M-theory. In this framework, the fundamental constituents of the universe aren't point-like particles, but tiny, one-dimensional vibrating strings. Different vibrational patterns of these strings give rise to different particles, including the graviton, the hypothetical quantum particle of gravity. String theory offers a way to describe gravity at the quantum level, and importantly, it suggests that the information about what falls into a black hole might not be lost. Instead, it could be stored or encoded on the event horizon itself, much like data on a holographic plate. This concept is often referred to as the holographic principle. Imagine that the three-dimensional reality we experience is actually a projection of information encoded on a two-dimensional surface, much like a hologram. Applied to black holes, this principle suggests that all the information about the matter that has ever fallen into the black hole might be imprinted on the two-dimensional surface of its event horizon. When the black hole evaporates via Hawking radiation, this encoded information might slowly leach out, perhaps in a highly scrambled form but fundamentally preserved. It's a bit like saying the entire contents of a 3D room could be fully described by patterns on its 2D walls. Mind-bending, isn't it? Another approach is loop quantum gravity, which attempts to quantize space-time itself, proposing that space and time are not continuous, but are made up of discrete fundamental loops or atoms of space-time. In this view, the singularity, that point of infinite density, might not truly exist. Instead, at the Planck scale, the smallest conceivable scale in physics, space-time might become granular, preventing the infinite compression and perhaps leading to a quantum bounce rather than a singular collapse. This could mean a black hole interior is not a point of no return, but a bridge to another region of space-time, or perhaps even another universe. These theories are incredibly complex and are still under active development, lacking definitive experimental verification. But they offer tantalizing glimpses into a future physics where the conflicts between general relativity and quantum mechanics are resolved. They hint at a universe far stranger and more interconnected than we currently comprehend. The black hole, therefore, is not merely a cosmic vacuum cleaner or a destructive force. It is a crucible, a natural laboratory operating at the very extremes of physics, forcing us to confront the deepest paradoxes of our universe. It challenges our most cherished theories and demands new ways of thinking. The journey into a black hole, conceptually speaking, is not just a descent into an abyss, but an ascent into the unknown frontiers of knowledge. It is a testament to the fact that even in the most hostile and mysterious corners of the cosmos, the universe whispers secrets that, if we're clever enough, we just might be able to decode. And as we continue our exploration, remember, the ultimate destination isn't just a point in space, but a profound shift in our understanding of reality itself. We've journeyed to the brink, peered into the abyss, and confronted the mind-bending reality of black holes. We've grappled with the information paradox, the no-hair theorem, and the terrifying elegance of Hawking radiation. But as profound as these concepts are, they merely hint at the ultimate frontier of our understanding, the point where the very fabric of physics, as we know it, unravels. We're talking about the singularity, that infinitely dense, infinitely curved heart of a black hole, where general relativity itself throws up its hands in despair. Imagine, if you will, standing at the edge of a cosmic chasm. You've seen the swirling vortex, felt the pull of the unknown, but you haven't yet plunged into the true depths where the rules change entirely. That's our next destination. We must confront the breakdown head-on, understand why our most cherished theories fail, and then explore the audacious new ideas scientists are devising to piece reality back together. At the singularity, general relativity, Einstein's masterful description of gravity as the curvature of spacetime reaches its mathematical limit. It predicts a point of infinite density and infinite curvature, a place where all matter is crushed into zero volume. But here's the rub. Infinities in physics are usually a red flag, a neon sign flashing error, theory incomplete. They tell us that our current understanding is insufficient, that there's a deeper layer of reality we haven't yet uncovered. It's like trying to describe the individual atoms in a solid object using only the laws of fluid dynamics. The scale is wrong, the tools are inadequate. For decades, this singularity has been the ultimate stumbling block, the cosmic brick wall where the smooth, elegant curves of general relativity collide violently with the chaotic, probabilistic world of quantum mechanics. On the grand scale of planets, stars, and galaxies, general relativity reigns supreme, describing gravity with breathtaking accuracy. But when you shrink down to the subatomic realm, to the incredibly tiny, discrete packets of energy and matter, quantum mechanics takes over, describing a universe of probabilities, wave functions, and fundamental uncertainty. The problem, as you might have gathered, is that black holes force these two titans of physics into an unavoidable confrontation. At the singularity, all the mass of a collapsed star is crammed into a space so unimaginably small that quantum effects must become dominant. Yet gravity, the domain of general relativity, is also at its most extreme. This is the ultimate wrestling match, and right now neither theory has a clear path to victory or even a way to share the ring. What we need desperately is a unified theory of quantum gravity, a single coherent framework that can describe gravity at both the grand cosmic scale and the minuscule quantum scale. This quest for quantum gravity leads us to some of the most profound and speculative ideas in modern physics, theories that push the boundaries of our imagination and challenge our very perception of reality. Let's dive into some of the leading contenders, starting with the idea that suggests our universe might be made of tiny vibrating strings. String theory, the universe as a cosmic symphony. Imagine for a moment that the fundamental building blocks of our universe aren't point-like particles, tiny indivisible dots of matter. Instead, picture them as incredibly small one-dimensional vibrating strings. That's the core premise of string theory. Just as different vibrations on a violin string produce different musical notes, different vibrational patterns of these fundamental cosmic strings give rise to different particles. An electron might be one vibrational mode, a photon another, and, crucially for our discussion, the graviton, the hypothetical quantum particle that mediates gravity, yet another. The elegance of string theory is that it naturally incorporates gravity into its framework. Unlike previous attempts to quantize gravity, which often led to mathematical infinities and inconsistencies, string theory provides a consistent way to describe all fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, within a single unified theory. It effectively smears out the point-like interactions, thereby avoiding the troublesome infinities that plague other approaches to quantum gravity. However, string theory comes with its own set of astonishing implications. For it to work mathematically, it requires the existence of extra spatial dimensions beyond the three we experience: up-down, left-right, forward-backward, and the one dimension of time. These extra dimensions, typically 6 or 7 of them, are thought to be compactified or curled up into incredibly tiny shapes, so small that we can't detect them directly. Think of a garden hose. From far away it looks like a one-dimensional line, but up close you see its two-dimensional circular cross-section. The extra dimensions are like that hidden circular cross-section, too small for us to perceive. For black holes, string theory offers a tantalizing solution to the information paradox. Remember Bekenstein and Hawking's discovery that black holes have entropy, a measure of their internal disorder, proportional to their event horizon's surface area? String theory provides a way to count the specific microscopic configurations, the microstates of the vibrating strings, that correspond to a black hole of a given mass, charge, and spin. This statistical mechanics explanation for black hole entropy, first achieved for a certain class of black holes, was a monumental success. It strongly suggests that information isn't truly lost. Rather, it's encoded in the intricate quantum states of these strings at the event horizon. The black hole in this view isn't a simple featureless void, but a complex vibrating collection of fundamental strings, preserving the very information it seems to swallow. The holographic principle, a universe on the edge. Building on the insights from black hole thermodynamics and string theory, another revolutionary idea emerged: the holographic principle. This concept, championed by physicists like Gerard 't Hooft and Leonard Susskind, is mind-boggling in its simplicity and profound in its implications. It suggests that the entire three-dimensional information content of a region of space can be fully described by data encoded on a two-dimensional surface that bounds that region. Think of a hologram. It's a 2D image that contains all the information needed to reconstruct a full 3D scene. The holographic principle proposes that our entire universe might be like a giant hologram. All the information about everything that happens within a volume of space, every particle, every interaction, every star, every galaxy, could, in principle, be encoded on its boundary surface. Where did this radical idea come from? It's directly inspired by black holes. The fact that a black hole's entropy scales with its surface area, the event horizon, not its volume, was a crucial clue. If a black hole is the densest possible storage device for information, and its capacity is limited by its surface area, then perhaps this is a fundamental property of reality itself. The maximum amount of information that can be contained in any region of space is proportional to the area of its boundary. For the information paradox, the holographic principle offers a compelling resolution. It suggests that the information about anything that falls into a black hole isn't discrete, but is instead imprinted or projected onto the event horizon. As Hawking radiation slowly causes the black hole to evaporate, this encoded information might slowly leak out, preserving the quantum integrity of the universe. The black hole, far from being a cosmic shredder, becomes a cosmic projector, displaying the universe's information on its boundary. This principle not only offers a potential solution to the information paradox, but also suggests that our perception of a three-dimensional universe might be an emergent phenomenon, a projection from a more fundamental two-dimensional reality. It's like living inside a video game, where the complex 3D world you experience is rendered from underlying 2D code. The implications for our understanding of reality, space, and time are staggering. Loop quantum gravity, the granular spacetime. While string theory and the holographic principle are deeply intertwined, another major contender for a theory of quantum gravity takes a very different approach. Loop quantum gravity, LQG. Instead of starting with fundamental strings, LQG begins by attempting to quantize spacetime itself. Imagine spacetime not as a smooth, continuous fabric, but as a finely woven, granular structure, like a piece of cloth made of countless tiny, discrete loops or quanta of space. In LQG, space and time are not infinitely divisible. They have a fundamental, smallest possible unit. There's a minimum possible area and a minimum possible volume. This quantization of space-time is a direct consequence of applying quantum mechanics to general relativity. Just as energy, light, and matter are quantized, LQG proposes that space itself comes in discrete packets. This means that at the incredibly small Planck scale, the realm where quantum gravity effects are expected to dominate, far smaller than an atom or even an atomic nucleus, spacetime would no longer be smooth but rather a foamy pixelated network of these loops. The profound implication for black holes is that the singularity, that problematic point of infinite density, might not actually exist. If space itself is granular, there's a minimum size it can take. Matter can't be compressed into truly zero volume. Instead, LQ suggests that the singularity is replaced by a region of extremely dense but finite space-time curvature, perhaps a Planck star or a fuzzball of quantum loops. Instead of being crushed out of existence, matter might reach an ultimate density and then bounce back, potentially even leading to the creation of a white hole, the theoretical opposite of a black hole from which matter can only exit. LQG offers a compelling alternative to string theory. It doesn't require extra spatial dimensions, and it directly addresses the quantization of space-time, providing a framework where the singularity is resolved by the very nature of space itself. However, it faces its own challenges, such as integrating the other fundamental forces and making concrete, experimentally verifiable predictions that can distinguish it from other theories. The frontier of the unknown. These theories, string theory, the holographic principle, and loop quantum gravity, represent our best current attempts to reconcile the seemingly irreconcilable worlds of the very large and the very small. They are highly mathematical, deeply complex, and still very much under construction. We don't yet have experimental evidence to definitively confirm any of them, and it's possible that the ultimate theory of quantum gravity will incorporate elements from all of them, or be something entirely different that we haven't even conceived of yet. What we do know is that black holes are the ultimate laboratories for these ideas. They are the only places in the universe where such extreme gravitational forces meet such incredibly small scales, forcing general relativity and quantum mechanics into a head-on collision. The breakdown of physics at the singularity is not a dead end. It's an open invitation, a cosmic puzzle demanding a new, more complete understanding of reality. Our journey into the heart of a black hole, therefore, isn't just a physical descent into an exotic celestial object. It's a philosophical exploration, a quest to redefine the very nature of space, time, matter, and information. It challenges our assumptions, expands our minds, and reminds us that the universe is far stranger, more intricate, and more awe-inspiring than we could ever imagine. The breakdown isn't an end, it's the beginning of a new chapter in physics, a chapter we are still very much writing. Our journey through the mind-bending physics of black holes has brought us to the very edge of human understanding, hasn't it? We've seen how these cosmic behemoths act as ultimate laboratories, pushing the boundaries of general relativity and quantum mechanics to their breaking points. We've touched upon the speculative solutions, string theory, the holographic principle, loop quantum gravity, each offering a tantalizing glimpse into a potential unified theory. But here's the rub, the grand challenge that keeps physicists up at night. How do we test these theories? How do we move beyond elegant mathematical frameworks and thought experiments to find concrete evidence? The truth is, the conditions required to observe quantum gravitational effects are so extreme, so utterly beyond our current technological capabilities, that they might as well be in another universe. Think about it. We're talking about the Planck scale. This isn't just small, it's incomprehensibly small. If we were to imagine an atom as the size of the entire observable universe, then a Planck length would be roughly the size of a single atom within that universe. That's the scale where space-time itself is theorized to become foamy, granular, and quantum. To probe such scales, we would need particle accelerators with energies so immense they would dwarf anything we've ever conceived. The Large Hadron Collider, for all its marvel, is a mere toy in comparison. It's like trying to understand the intricate workings of a microchip using only a magnifying glass. We're simply not equipped to see the quantum fabric of space-time directly. This makes the quest for quantum gravity a unique blend of profound theoretical insight and a frustrating lack of experimental verification. We construct these magnificent intellectual cathedrals, but the tools to truly walk through their doors remain elusive. And it's precisely at this juncture, where theory outstrips observation, that the information paradox looms largest, casting a long shadow over our understanding of black holes and indeed the very nature of reality. We discussed it before, this fundamental conflict. General relativity suggests information about matter falling into a black hole is irrevocably lost, forever swallowed by the singularity. Quantum mechanics, on the other hand, staunchly insist that information can never be truly destroyed. It must always be conserved, merely transformed. This isn't just an academic squabble. It strikes at the heart of what we believe about the universe. If information is lost in black holes, then the universe isn't deterministic in the way quantum mechanics implies. If it's conserved, then our understanding of black holes and space-time needs a radical overhaul. Stephen Hawking himself initially championed the idea of information loss, only to later concede that it must be preserved. But how? That remains the million-dollar question. This paradox became even more acute, even more unsettling, with the introduction of what's known as the firewall paradox. Imagine, if you will, the event horizon. For decades following Einstein's equivalence principle, we've believed that crossing the event horizon of a large black hole would be a perfectly smooth, uneventful experience for an infalling observer, at least until the tidal forces of spaghettification took over much later. You wouldn't feel anything special, you'd just cross a point of no return. This is a cornerstone of general relativity. But what if that wasn't true? What if, in order to preserve information, the event horizon itself wasn't smooth? Here's the premise. If information is indeed conserved and eventually re-emitted via Hawking radiation, then that information has to be stored somewhere near the black hole. Some physicists, trying to reconcile the information paradox, propose that the event horizon isn't just a one-way membrane, but a place where quantum information is processed. If you try to encode all the information of what's fallen into the black hole onto the event horizon, as the holographic principle might suggest, and then combine that with the idea of Hawking radiation carrying information away, you run into a very serious problem. To ensure information conservation, some theories suggest that the event horizon must act as a sort of quantum entanglement firewall. Instead of a gentle, uneventful crossing, an infalling observer would encounter a region of extremely high-energy particles, a literal wall of fire, or rather, a region of intense quantum activity that would instantly incinerate them. Can you feel the intellectual whiplash? On one hand, Einstein's equivalence principle tells us that the event horizon of a large black hole should be perfectly benign, locally indistinguishable from empty space. On the other hand, the firewall paradox suggests that if information is to be preserved, this gentle crossing is a myth, replaced by a violent, destructive barrier. It's a direct, head-on collision between two fundamental pillars of modern physics: the equivalence principle of general relativity and the information conservation principle of quantum mechanics. This isn't just a theoretical curiosity, it forces us to make an agonizing choice. Does information truly get destroyed violating quantum mechanics? Or does the equivalence principle, the very foundation of our understanding of gravity, break down at the event horizon? Or is there some entirely new, unimaginable physics at play that allows for both? The implications are profound. If the equivalence principle is violated, it means that gravity behaves in ways we simply don't understand, even in regions where space-time curvature isn't infinite. It would challenge our entire framework for describing how objects fall and how spacetime works. If information is lost, it means a fundamental tenet of quantum mechanics is wrong, and the universe is far less predictable and orderly than we thought. So where do we stand today in this cosmic tug-of-war? The firewall paradox remains one of the most hotly debated topics in theoretical physics. There are arguments for and against its existence with various proposed resolutions. Some physicists suggest that the information is encoded in a subtle way that doesn't create a firewall. Others propose that the paradox itself points to a deeper misunderstanding of quantum gravity, hinting at new physics we haven't even begun to conceive. This isn't a sign of failure, though. Far from it. This is physics in action, pushing the absolute limits of our knowledge. These paradoxes are not roadblocks. They are signposts pointing us toward the next great revolution in our understanding of the universe. They force us to question our deepest assumptions and to seek a more complete, unified theory that can gracefully reconcile these seemingly contradictory principles. The quest for quantum gravity, for a theory that can describe the universe from the largest scales of galaxies to the smallest, most fundamental quantum foam, continues with renewed urgency. Black holes, these enigmatic cosmic monsters, remain at the heart of this quest. They are the ultimate proving ground, the theoretical crucible where our most cherished scientific principles are tested, strained, and sometimes spectacularly broken. We may not have the experimental tools to directly observe the Planck scale or witness the creation of a firewall, but the intellectual struggle to resolve these paradoxes is, in itself, a journey of discovery. It's a testament to the human spirit's insatiable curiosity, our unyielding desire to peer into the deepest mysteries of existence and understand the fundamental laws that govern our reality. And as we continue this journey, remember, the universe is always ready to surprise us, to challenge our assumptions, and to reveal wonders far stranger and more beautiful than we could ever imagine. The answers, though elusive, are out there waiting for us to unravel them. We left off staring into a quantum abyss, didn't we? The firewall paradox presented us with an agonizing choice. Either sacrifice Einstein's beautifully smooth space-time where an infalling observer crosses the event horizon without a hitch, or surrender the sacred principle of quantum information conservation, which dictates that information can never truly be destroyed. It's not just a theoretical skirmish among physicists. It's a profound crisis for our understanding of reality itself, a cosmic riddle etched into the very fabric of existence. This isn't just about what happens to the poor astronaut or the drop dictionary. It's about the fundamental rules governing our universe. Think about it. Every interaction, every particle, every quantum state leaves an indelible mark. If information could simply vanish into a black hole lost forever, then the universe wouldn't be deterministic in the way quantum mechanics suggests. It would be fundamentally unpredictable, losing its memory, its very blueprint. This isn't just inconvenient, it's catastrophic for the mathematical elegance and predictive power of our most successful theories. Black holes, then, aren't just cosmic vacuum cleaners. They are cosmic laboratories, forcing us to confront the limits of our knowledge, pushing our most cherished principles to their absolute breaking point. So how do we resolve this cosmic tug-of-war? How do we reconcile the smooth, predictable space-time of general relativity with the information-preserving, quantum weirdness of the subatomic world? This is where the landscape of theoretical physics truly blossoms into a garden of mind-bending possibilities, each striving to paint a more complete picture of what happens at the very edge of reality. One of the most intriguing and perhaps most radical proposals comes from the realm of string theory. We've touched upon string theory before, envisioning fundamental particles not as points but as tiny vibrating strings. Now, let's see how it tackles the black hole problem head-on. offering a potential resolution not just to the information paradox, but even to the dreaded singularity itself. Imagine, if you will, that a black hole isn't an empty region of space surrounding an infinitely dense point. What if instead a black hole is the quantum information? This is the core idea behind our fuzzballs. Forget the classical picture of a black hole with a sharp, distinct event horizon and a singularity lurking in the center. In the fuzzball model, a black hole is a dense, quantum-entangled fuzzball of strings, a complex, high-energy quantum state of spacetime itself. Think of it like this. Instead of a perfectly smooth, hard-shelled fruit with a tiny seed inside, imagine a fruit that's entirely made of its fuzzy skin, extending all the way to its core. There's no distinct boundary between the skin and the inside because it's all skin. Similarly, in the fuzzball paradigm, the black hole's entire interior, including where the singularity would normally be, is replaced by this intricate quantum-entangled fuzz. The event horizon isn't a sharp boundary you cross, it's simply the fuzzy quantum surface of this object. How does this resolve our paradoxes? First, the singularity problem. If the black hole is a fuzzball, there's no point of infinite density. Instead, the matter that collapses to form the black hole is converted into this dense, complex, quantum state of strings, distributing its energy and information across the entire volume of the fuzzball. There's no point where physics breaks down, because the matter never truly collapses to zero volume. Second, and crucially, the information paradox. The information isn't lost, because it's encoded directly into the intricate quantum state of the fuzzball itself. It's like dropping a book into a very, very complex three-dimensional quantum-entangled sponge. The book doesn't disappear, its information is absorbed and re-encoded into the specific configurations and vibrations of the sponge's fibers. When Hawking radiation eventually causes the fuzzball to evaporate, this encoded information is slowly released, preserving the quantum mechanics principle that information is never truly destroyed. And what about the firewall paradox? If the event horizon is replaced by the surface of this fuzzball, there's no sharp, violent boundary to incinerate you. Instead, you'd slowly, perhaps even gently merge with the quantum fuzz, becoming part of its intricate, information-rich structure. The smooth crossing predicted by Einstein's equivalence principle would be preserved, albeit in a radically different quantum mechanical context. It's not a void you enter, but a complex quantum mechanical object you join. This brings us back to the holographic principle, which we touched upon earlier. With fuzzballs, the holographic principle takes on an even more profound meaning. If the black hole is a fuzzball, and all the information about its interior is encoded in the quantum state of its surface, then it's a literal realization of the holographic idea. The entire three-dimensional volume of the black hole, and all the information it contains, can be described by what's happening on its two-dimensional boundary. This isn't just a clever analogy, it's a radical proposal that our entire three-dimensional reality, the universe we perceive with all its depth and complexity, might itself be an emergent property of information stored on a two-dimensional boundary, perhaps at the very edge of the cosmos. If this is true, then space and time as we understand them aren't fundamental building blocks of reality, but rather derived concepts, much like the image projected onto a screen from a flat film. Imagine the implications for our understanding of existence. Are we living in a cosmic hologram? The very notion challenges our deepest intuitions about what is real. While string theory offers fuzzballs, another contender in the quest for quantum gravity, loop quantum gravity, LQG, offers a different, yet equally revolutionary approach to the singularity problem. Instead of strings, LQG posits that space-time itself is not a continuous fabric but granular, made up of tiny, discrete loops or quanta. Think of space-time not as a smooth canvas, but as a finely woven tapestry. In this framework, when matter collapses under its own immense gravity, it can't simply compress to an infinitely dense point. Just as there's a limit to how small you can make a pixel on a screen, there's a fundamental minimum size for these space-time loops. At the center of a black hole, according to LQG, gravity becomes so strong that space-time itself resists further compression. Instead of collapsing to a singularity, it might undergo a quantum bounce. Imagine a cosmic trampoline. When you jump on it, it stretches, but there's a limit to how far it can stretch before it pushes back. Similarly, space-time, when pushed to its limits inside a black hole, might bounce back, potentially avoiding the singularity altogether. What happens to the matter and information then? Some theories suggest that the black hole might act as a portal to another region of space-time, perhaps even another universe, or that the matter simply reverses its collapse and expands again. Information in this scenario would not be lost, but transformed and passed through this quantum bounce. These aren't just academic exercises in theoretical physics, they are attempts to redefine our understanding of the universe's most fundamental building blocks: space, time, matter, and energy. They push us to consider a reality far stranger and more intricate than anything we could have imagined from our everyday experiences. But here's the rub, the grand challenge that keeps physicists awake at night. How do we verify any of this? These theories operate at the Planck scale, an incomprehensibly tiny realm far beyond the reach of our current observational capabilities. We can't build a particle accelerator large enough to probe these dimensions, nor can we directly observe the quantum fuzz of a black hole. It's like trying to study the individual threads of a tapestry from orbit. So how do we test these ideas? The answer lies in indirect observations and the relentless pursuit of theoretical consistency. We look for subtle signatures and gravitational waves that might hint at the granular nature of space-time, or anomalies in the cosmic background radiation that could be echoes of quantum bounces. We refine our mathematical models, searching for internal contradictions or unexpected predictions that could be tested in other ways. Black holes in this sense become our ultimate theoretical laboratories. They are the only places in the universe where these extreme conditions naturally occur, where the laws of general relativity and quantum mechanics are forced to collide, offering us a glimpse into the unified theory we so desperately seek. The quest for a unified theory, a theory of everything that seamlessly combines general relativity and quantum mechanics, is the holy grail of modern physics. Black holes represent both the greatest obstacle and the most promising pathway to this ultimate understanding. They are cosmic paradoxes that demand a new physics, a new language to describe reality. Our journey into the black hole is, in essence, a journey into the very nature of reality itself. It forces us to question what is fundamental and what is emergent, what is continuous and what is discrete, what is lost and what is preserved. The answers remain elusive, hidden within the extreme curvature of space-time and the quantum foam of existence. But the pursuit of these answers, the relentless push against the boundaries of the unknown, is what defines us as curious, intelligent beings. The universe, in its profound mystery, continues to invite us to rewrite the rules, to expand our understanding, and to marvel at the sheer audacity of existence. The next chapter of physics is waiting to be written, and black holes are holding the pen. We've journeyed deep into the heart of darkness, haven't we? Through event horizons and beyond, tracing the theoretical pathways of space-time warped to its absolute limit. We've grappled with concepts that challenge our very understanding of reality, from the crushing embrace of spaghettification to the mind-bending implications of information loss. But as we stand at the precipice of these cosmic enigmas, a crucial truth becomes glaringly clear. Black holes aren't just fascinating curiosities, they are the ultimate battlegrounds where our most cherished scientific theories clash, and where often they break down entirely. Think back to our initial explorations. We marvelled at Einstein's general relativity, a theory of breathtaking elegance that describes gravity not as a force, but as the curvature of space-time itself. It painted a picture of the cosmos as a dynamic, flexible fabric, where massive objects create dips and valleys, guiding the paths of everything around them. This theory, incredibly successful in describing everything from planetary orbits to the expansion of the universe, is the bedrock upon which our understanding of black holes rests. It tells us about the event horizon, the point of no return, and it predicts the existence of the singularity, a point of infinite density at the black hole's core. Yet, as we ventured closer, we encountered the other titan of modern physics, quantum mechanics. This theory governs the bizarre, probabilistic world of the very small, atoms, electrons, photons. It describes a universe where particles can be in multiple places at once, where observation changes reality, and where information fundamentally can never be destroyed. Quantum mechanics is the foundation of all modern technology, from smartphones to lasers, and it has passed every experimental test thrown at it with flying colours. Herein lies the profound, unsettling dilemma. General relativity, so magnificent on the grand cosmic scale, utterly collapses when confronted with the infinite density of the singularity. It simply doesn't have the mathematical tools to describe what happens when space-time is squeezed to an infinitely small point. It throws up its hands and says, "Here, be dragons." Simultaneously, quantum mechanics, so precise and predictive in the microscopic realm, struggles to incorporate gravity into its framework. It sees space-time as a smooth, continuous canvas, while quantum fluctuations suggest a grainy, foamy reality at the smallest scales. The black hole, then, isn't just a region where gravity is extreme. It's a cosmic crucible where these two pillars of physics are forced to interact, and in doing so reveal their profound incompatibility. They speak different languages, use different rulebooks, and offer conflicting descriptions of the same ultimate reality. Remember the information paradox? That gnawing question of what happens to all the unique data of everything a black hole swallows. General relativity, in its classic form, suggests that once something crosses the event horizon, all its intrinsic information, its quantum state, its history, its very identity, is lost forever, compressed into the generic characteristics of mass, spin, and charge, the no-hair theorem. But quantum mechanics screams in protest. Information cannot be destroyed. It must be conserved somewhere, somehow. This isn't just a minor disagreement. It's a fundamental contradiction that strikes at the heart of how we understand the universe. If information can be lost, then the very fabric of cause and effect, the predictability of quantum mechanics, begins to unravel. And what about the firewall paradox? That terrifying possibility that the event horizon, instead of being the smooth, uneventful crossing predicted by Einstein's equivalence principle, might actually be a violent, superheated quantum firewall. If information is indeed encoded on the event horizon, as the holographic principle hints, and if that information needs to be processed and released as a black hole evaporates via Hawking radiation, then the delicate balance of the equivalence principle is shattered. You, the intrepid traveller, would no longer just pass through an unnoticeable boundary, you'd be incinerated in an instant. This isn't just a bad day for an astronaut. It's a direct assault on one of the most fundamental tenets of general relativity, a principle that underpins our entire understanding of gravity and space-time. These aren't mere academic squabbles. These are deep fissures in our understanding of the cosmos. They tell us, unequivocally, that our current theories are incomplete. They signal a profound need for something more, something that can bridge the chasm between the very large and the very small, something that can describe gravity in the quantum realm and quantum phenomena in the gravitational realm. We need a unified theory of quantum gravity. Why is this so crucial, you might ask? Because without it, we cannot truly understand the universe's most extreme environments. We cannot fully comprehend the birth of the universe in the Big Bang, where all matter and energy were compressed into an incredibly dense hot state, much like a singularity. We cannot fully grasp the ultimate fate of black holes, or even the fundamental nature of space and time themselves at their most granular level. A theory of quantum gravity wouldn't just solve the black hole paradoxes, it would provide a more complete, consistent picture of reality, unifying the forces that govern everything we observe. Imagine for a moment what this new physics might entail. It's not just about adding a few new equations, it's about potentially re-evaluating our most basic assumptions about reality. What if space isn't continuous, but made of tiny, discrete loops, or atoms of spacetime, as loop quantum gravity suggests? What if, as string theory proposes, the fundamental building blocks of the universe aren't point-like particles, but tiny vibrating strings existing in extra dimensions we can't perceive? These aren't just wild speculations, they are serious attempts to reconcile the irreconcilable, to find a deeper layer of reality where the rules of general relativity and quantum mechanics emerge as different aspects of a single, more comprehensive truth. But how do we test these incredible ideas? This is where the challenge truly becomes monumental. The scales at which quantum gravity effects are predicted to become dominant are almost unimaginably small. The Planck length about 10 out of 35 meters, and the Planck time about 10^43 seconds. To probe these scales, we would need energies far beyond anything achievable in even our largest particle accelerators, like the Large Hadron Collider. It would be like trying to study the structure of an atom by smashing two galaxies together. The technology simply doesn't exist, and may never exist, to directly observe these phenomena. This is precisely why black holes become our invaluable, albeit theoretical, laboratories. They are the only places in the universe where the conditions naturally become so extreme that both general relativity and quantum mechanics are pushed to their breaking point simultaneously. They are the cosmic arenas where the effects of quantum gravity are no longer subtle, but potentially macroscopic enough to manifest as paradoxes like information loss or firewalls. By studying the theoretical implications of black holes, by pushing the boundaries of what our current physics can describe, we are forced to invent new physics. We're using these dark, enigmatic objects as thought experiments on an epic scale, guiding us toward a more complete understanding of the fundamental laws that govern our existence. We may not be able to send probes into a singularity, or directly observe the Planck scale, but we can use the perplexing behavior of black holes to infer what those fundamental laws must be. The quest for quantum gravity is the ultimate scientific adventure, a journey to reconcile the largest and the smallest, the heaviest and the lightest, the most elegant and the most chaotic aspects of our universe. It's a quest to understand not just what happens inside a black hole, but what happens at the very edges of reality itself. And as we continue to probe these cosmic mysteries, we remain driven by an insatiable curiosity, a shared wonder, and the profound realization that the answers we seek may redefine everything we thought we knew. The black hole, then, is not just an endpoint. It is a gateway to the next revolution in physics, a beacon guiding us toward a deeper, more unified understanding of the cosmos. We've peered into the profound depths of black holes, those cosmic behemoths that chew up and spit out our most cherished physical laws. We've wrestled with the mind-bending implications of the event horizon, the singularity, and the seemingly insurmountable paradoxes they present. But as we discussed, these aren't just cosmic curiosities, they are the ultimate proving grounds for an even grander theory: quantum gravity. The theories we touched upon, string theory, the holographic principle, loop quantum gravity, are all valiant attempts to bridge the most fundamental chasm in modern physics. They represent our efforts to understand what happens when the smooth, continuous fabric of space-time described by Einstein's general relativity meets the jittery, probabilistic realm of quantum mechanics. It's at the Planck scale, that unimaginably tiny frontier, where these two titans are forced to confront each other, and where our current understanding of reality utterly breaks down. But why is this unification so incredibly difficult? Why have generations of brilliant minds grappled with this problem without a definitive breakthrough? Imagine, if you will, two magnificent but entirely different languages. General relativity, the language of the cosmos, describes gravity not as a force, but as the curvature of space-time itself, a grand, elegant geometry that dictates the motion of planets, stars, and galaxies. It's a macroscopic theory dealing with vast scales, where everything is smooth, predictable, and deterministic. Then we have quantum mechanics, the language of the incredibly small. This is a world of probabilities, uncertainties, and discrete packets of energy. Here, particles pop in and out of existence, and nothing is truly fixed until it's observed. It describes the electromagnetic, strong and weak nuclear forces with astonishing precision. It's a microscopic theory, dealing with the fuzziness and inherent unpredictability of the subatomic realm. The problem arises because gravity, as described by general relativity, is a smooth, continuous field. But if we try to apply the rules of quantum mechanics to gravity, we expect gravity itself to be quantized, meaning the unit should come in discrete packets, or gravitons, much like light comes in photons. The equations for quantum gravity, however, become impossibly complex, and yield nonsensical infinities when we try to simply combine the two. It's like trying to describe the individual brushstrokes of a painting quantum mechanics, using only the broad, sweeping movements of a symphony, general relativity. They are fundamentally incompatible frameworks, yet they must both be true, and they must both apply to black holes. Think about it. A black hole compresses an immense amount of mass into an infinitesimally small volume, creating conditions where both extreme gravity, general relativity's domain, and quantum effects, quantum mechanics domain, are at play simultaneously. The singularity is the ultimate collision point, the cosmic crucible where these two languages must somehow speak to each other. So, what happens inside a black hole when physics truly breaks down, and how do these nascent theories of quantum gravity attempt to fix it? Let's revisit the singularity. In general relativity, it's a point of infinite density and infinite space-time curvature, a mathematical abyss where the laws of physics cease to function. But quantum mechanics abhors infinities. It suggests that at the Planck scale, there must be a fundamental limit to how small or dense something can become. This is where the concept of space-time foam, first envisioned by John Wheeler, comes into play. Imagine space-time not as a perfectly smooth, unblemished surface, but as something incredibly turbulent and frothy at the Planck scale. If you could zoom in far enough, past atoms, past quarks, past the smallest strings of string theory, you might see space-time itself bubbling and fluctuating, constantly changing its topology, forming tiny wormholes and baby universes. This space-time foam suggests that the singularity, rather than being an infinite point, might be a region where space-time becomes so warped and quantum that our classical notions of space and time simply dissolve. It's not a point of infinite density, but a region where the very fabric of reality is torn and rewoven on a quantum level. This leads us to an even more radical idea. What if space-time isn't fundamental at all? What if it emerges from something more basic, much like temperature emerges from the collective motion of countless atoms? This emergent spacetime concept is a cornerstone of some quantum gravity theories, particularly those influenced by the holographic principle. If spacetime itself is emergent, then the information paradox takes on a whole new dimension. Perhaps information isn't lost because it's encoded in the fundamental constituents from which spacetime itself arises. Consider the theories we discussed. String theory's fuzzballs. Instead of a singularity, the black hole's interior is a tangled, vibrating mess of fundamental strings. There's no smooth, empty space leading to a point. It's a dense, quantum-entangled ball of information. In this view, the event horizon isn't a sharp boundary, but the surface of this fuzzball, and information is stored within its complex quantum state, eventually radiating out as Hawking radiation. This elegantly resolves the information paradox by ensuring information never truly falls into a singularity, because there isn't one. Loop quantum gravity's quantum bounce. Here is granular, made of discrete loops. As matter falls into a black hole, it doesn't compress infinitely. Instead, the quantum nature of spacetime creates a repulsive force at incredibly high densities, preventing a singularity. What happens then? The theory suggests a quantum bounce. Matter might rebound and emerge into another region of spacetime, perhaps even another universe. This is a mind-blowing concept, implying black holes could be portals, not just cosmic dead ends, and that information is preserved by being transported. The holographic principle. This principle, while not a full theory of quantum gravity itself, is a profounder insight that guides many of them. It suggests that the 3D information of a volume of space, like the interior of a black hole, can be fully encoded on a 2D surface, such as the event horizon. If this is true, then the information isn't lost inside, it's always written on the boundary. This means the very nature of reality might be fundamentally holographic, a projection from a lower dimensional source. So from these perspectives, the inside of a black hole transforms from a terrifying, destructive singularity into something far more intricate and dynamic. It's not necessarily an endpoint, but a region of extreme quantum processing. The event horizon, too, might not be the classical smooth one-way membrane Einstein envisioned. If the firewall paradox is correct, and information must be conserved, then the event horizon itself becomes a violent quantum-entangled boundary, a firewall that incinerates anything that tries to cross it. This would mean that our journey across the event horizon, which we previously imagined as potentially smooth for a supermassive black hole, would instead be instantaneously catastrophic. The implications are staggering. If the event horizon is a firewall, then Einstein's equivalence principle, the idea that free fall is indistinguishable from zero gravity, breaks down at this critical boundary. This forces us to make an agonizing choice. Either information is lost, or the equivalence principle, a cornerstone of general relativity, is violated. This is the profound dilemma at the heart of the firewall paradox, and it's a direct consequence of trying to reconcile quantum mechanics with gravity. You see, black holes aren't just tearing apart matter, they are tearing apart our most fundamental theories. They force us to confront the fact that our current understanding of the universe is incomplete, perhaps even contradictory, at its most extreme limits. But how do we ever test these wild, speculative ideas? We can't build a particle accelerator large enough to reach the Planck scale. We can't send probes into a black hole and expect them to send back data. The very nature of black holes, with their event horizons, makes direct observation of their interiors impossible. This is where the ingenuity of theoretical physics truly shines. We look for indirect evidence. We demand mathematical consistency. Any proposed theory of quantum gravity must seamlessly transition back to general relativity at large scales and to quantum mechanics at small scales, where those theories are known to work. We search for subtle, observable signatures that might distinguish one theory from another. Could gravitational waves carry a faint echo of a quantum bounce? Could extremely precise measurements of Hawking radiation reveal patterns that hint at the internal structure of a fuzzball? Could future astronomical observations of black hole mergers or extreme environments offer clues? For now, black holes remain our greatest theoretical laboratories. They are cosmic thought experiments that push us to redefine space, time, matter, and information in ways we are only just beginning to comprehend. The quest for quantum gravity isn't just about understanding black holes, it's about unlocking the deepest secrets of the universe, revealing the true nature of reality itself. It's a journey into the unknown, guided by logic, mathematics, and an insatiable curiosity about what lies beyond the veil of our current knowledge. And as we venture further, we find that the line between what is scientifically plausible and philosophically profound becomes increasingly blurred. We've journeyed through the mind-bending landscape of quantum gravity theories, peering into the theoretical solutions that attempt to reconcile the seemingly irreconcilable worlds of general relativity and quantum mechanics. We've seen how string theory, with its vibrating fundamental strings, proposes a fuzzball black hole where information is preserved. We've explored the holographic principle, suggesting our reality might be a projection from a boundary. And we've touched upon loop quantum gravity, which replaces the singularity with a quantum bounce, hinting at a possible rebound into another cosmic existence. These are not just fascinating thought experiments, they are humanity's boldest attempts to answer the deepest questions about the universe. But as we stand at this precipice of theoretical understanding, a crucial question looms large. How do we test these ideas? How do we move from elegant mathematics and compelling narratives to verifiable scientific fact? The challenge, my friends, is monumental. These theories operate at scales so infinitesimally small, the Planck scale, that our most powerful particle accelerators, like the Large Hadron Collider, can't even begin to probe them. We're talking about distances a billion times smaller than a proton, and energies far beyond anything we can generate on Earth. It's like trying to understand the intricate dance of atoms within a single grain of sand by observing a hurricane from space. The tools we have simply aren't designed for that level of microscopic detail. So while these theories offer potential resolutions to the information paradox and the singularity problem, they remain largely speculative, awaiting either a revolutionary new experimental technique or a profound theoretical breakthrough that provides testable predictions at more accessible scales. It's a testament to the sheer ingenuity and frustration of modern physics. Yet the questions persist. If the singularity isn't truly a point of infinite density, what is it? If information isn't destroyed, where does it go? And what if black holes aren't just cosmic dead ends, but something far more profound, perhaps even gateways? This brings us to one of the most tantalizing and speculative ideas in theoretical physics, the concept of wormholes and the possibility of baby universes. Imagine, if you will, that the fabric of space-time isn't just curved by mass and energy, but can also be folded and stitched in ways we can barely comprehend. Wormholes, also known as Einstein-Rosen bridges, are theoretical shortcuts through space-time. They are solutions to Einstein's equations of general relativity, much like black holes are. Picture our universe as a vast, two-dimensional sheet. To travel from point A to point B, you typically have to traverse the surface. But if you could fold that sheet and create a tunnel connecting A and B, you could cross the immense distance almost instantaneously. That's the essence of a wormhole, a tunnel connecting two distinct regions of space-time, possibly even two different universes. Now here is where it gets truly mind-bending. While theoretically possible, these wormholes are generally unstable. They would likely collapse faster than anything could traverse them, or they'd be so tiny that nothing larger than a subatomic particle could pass through. To keep a wormhole open and traversable, you would need something truly exotic, negative energy or exotic matter. Matter with properties unlike anything we've ever observed, which exerts a repulsive gravitational force. While some quantum phenomena hint at the possibility of localized negative energy densities creating enough of it to prop open a cosmic tunnel remains firmly in the realm of science fiction. However, the idea of black holes being connected to something else lingers. What if the singularity, that point where our physics breaks down, isn't just an endpoint, but a transition point? This is where the concept of baby universes comes into play, particularly echoing ideas from loop quantum gravity. Imagine all the matter and energy swallowed by a black hole. Instead of being crushed into an infinitely dense point, the quantum nature of spacetime as suggested by LQG might prevent infinite compression. At the Planck scale, spacetime itself becomes granular, preventing a true singularity. What if instead this incredibly dense, highly compressed matter and energy undergoes a quantum bounce? This bounce wouldn't send it back into our universe. Instead, it could potentially expand into an entirely new, separate region of spacetime, a sort of baby universe. Think of it like this. Our universe might have begun with a big bang, an incredibly dense point that expanded rapidly. What if the singularity within a black hole is, in essence, a localized Big Bang for another universe? All the information, all the mass energy that falls into our black hole wouldn't be lost. It would simply be recycled, re-emerging as the raw material for a new cosmic entity, perhaps with its own unique physical laws and dimensions. This idea offers an elegant, albeit highly speculative resolution to the information paradox. The information isn't destroyed, it simply exits our universe and seeds another. From our perspective, the information is lost, but from a cosmic, multi-universal perspective, it's merely transferred. Black holes, then, wouldn't just be destroyers of worlds, they could be cosmic wombs, birthing new realities beyond our observational reach. This concept naturally leads us to the broader whole multiverse hypothesis. If black holes can spawn new universes, then our own universe might itself be a baby universe, born from a black hole in a larger parent universe. This isn't just a philosophical fancy, it's a profound implication of some of our most advanced physical theories, pushing the boundaries of what we consider reality. It suggests that the cosmos we inhabit might just be one bubble in an infinite frothing ocean of realities, each potentially connected to others through the enigmatic portals of black holes. Of course, these are grand, sweeping ideas, far removed from direct observation. So, as physicists continue to grapple with these theoretical behemoths, the scientific community is also making incredible strides on another front. Observing black holes. While we can't yet peek into a singularity or travel through a wormhole, we are getting closer than ever to understanding the edges of these cosmic titans. Consider the revolution of what gravitational wave astronomy. When two black holes collide and merge, they send ripples through the very fabric of space-time, gravitational waves, that we can now detect here on Earth using instruments like LIGO and Virgo. These detections have given us empirical evidence of black hole mergers, allowing us to measure their masses, spins, and how they distort space-time in their violent dance. This isn't quantum gravity, but it's general relativity operating in its most extreme dynamic regime, confirming our understanding of these objects' incredible power and allowing us to probe their properties with unprecedented precision. And then there's the Event Horizon Telescope, EHT. Remember our discussion about the event horizon, the point of no return? For decades it remained an abstract boundary, but in 2019 and again in 2022, the EHT collaboration delivered something truly astonishing. the first direct images of black hole shadows. We saw the supermassive black hole at the centre of the galaxy M87, and then our own Milky Way's central behemoth Sagittarius A. What we're seeing in these images isn't the black hole itself, which is truly black, but rather the silhouette it casts against the glowing superheated gas swirling around it. This shadow is defined by the event horizon, warped by intense gravity. These images are monumental. They allow us to test general relativity in the strongest gravitational fields imaginable, right at the doorstep of the event horizon. They confirm Einstein's predictions about how light bends around these objects and allow us to measure the black hole's sizes and shapes with remarkable accuracy. These observational breakthroughs are crucial because they provide anchor points for our theories. They tell us what is happening at the observable limits of a black hole, helping to constrain the wilder theoretical possibilities. We can't yet see the singularity. We can't yet confirm wormholes or baby universes, but we are seeing the direct influence of these objects on the cosmos around them. We are observing the consequences of space-time warping to an unimaginable degree. So where does that leave us? We stand at a thrilling intersection of theory and observation. On one hand, we have brilliant minds crafting mathematical frameworks that push the very limits of our imagination, suggesting that black holes might be gateways to other universes or repositories of information in forms we can barely grasp. On the other hand, we have cutting-edge instruments that are finally allowing us to see these cosmic behemoths, providing empirical data that grounds our understanding and helps us refine our models. The journey into a black hole is ultimately a journey into the unknown. It forces us to confront the very limits of our current physics, demanding that we invent new ways of thinking, new theories, and new observational techniques. Black holes are not just cosmic vacuum cleaners, they are cosmic laboratories, forcing us to redefine our understanding of space, time, matter, and information itself. They are the ultimate frontier, challenging us to expand our minds and embrace the profound strangeness of the universe we inhabit. And the quest to unravel their deepest secrets, my friends, is far from over. We've journeyed through the cosmos, peered into the darkest corners of space-time, and grappled with concepts that redefine our very understanding of reality. From the elegant curvature of space-time predicted by Einstein to the mind-bending quantum foam of the Planck scale, black holes have served as our ultimate cosmic laboratory, pushing the boundaries of what we thought possible and forcing us to confront the profound limitations of our current physics. We've seen how these enigmatic behemoths aren't just cosmic vacuum cleaners, but critical battlegrounds where the two pillars of modern physics, general relativity and quantum mechanics, clash in a spectacular unresolved conflict. Now, as we stand at the precipice of the unknown, it's time to consider the grander implications of this cosmic drama. What does it truly mean that our most successful theories break down at the heart of a black hole? What does the quest to understand these objects tell us about the ultimate nature of our universe? And where do we go from here in our pursuit of a unified theory? The dream of a theory of everything isn't new. For centuries, physicists have striven to unify disparate forces and phenomena under a single elegant framework. Newton united the heavens and the earth with his law of universal gravitation. Maxwell wove together electricity and magnetism into a single electromagnetic force, revealing light itself as an electromagnetic wave. Einstein, in his special and general theories of relativity, showed us the deep connection between space, time, matter, and energy. Each step was a profound leap, simplifying our understanding of the universe, revealing an underlying order that was both beautiful and powerful. But the atom, and later the subatomic world, presented new challenges. The strong and weak nuclear forces, governing the behavior of particles within the nucleus, refused to be integrated into Einstein's gravitational tapestry. And then came the black hole, a cosmic crucible where gravity becomes so extreme that it can no longer be ignored in the quantum realm. It's here, at the singularity, or at the event horizon if the firewall paradox holds true, that the need for a unified theory of quantum gravity becomes not just desirable but absolutely essential. Black holes are the ultimate tests, the cosmic pressure cookers designed to break our theories and show us the way forward. Imagine, if you will, a universe where all forces, gravity, electromagnetism, and the strong and weak nuclear forces are merely different manifestations of a single, underlying reality. This is the promise of quantum gravity, and black holes are the keys to unlocking it. String theory, with its vibrating fundamental strings and extra dimensions, offers a tantalizing vision where black holes are not singularities but fuzzballs, holographic projections of quantum information. Loop quantum gravity, with its granular spacetime, suggests a universe that bounces rather than collapses, perhaps giving birth to new realities. These aren't just abstract mathematical constructs, they're attempts to redefine the very fabric of existence. Consider the holographic principle once more. It's not just a clever way to resolve the information paradox, it's a radical reimagining of reality itself. If all the information contained within a three-dimensional volume can be encoded on its two-dimensional boundary, what does that imply about our perceived three-dimensional world? Are we living in a cosmic hologram? This isn't science fiction, it's a profound implication emerging directly from the physics of black holes. The event horizon, that seemingly simple boundary of no return, might actually be a cosmic screen projecting the reality we experience. It suggests that the universe might be fundamentally flatter, more interconnected, and far stranger than we ever imagined. The depth and solidity we perceive could be an emergent property, an illusion born from information encoded on a distant surface. And what of the quantum bounce proposed by loop quantum gravity? The idea that the singularity isn't an endpoint, but a moment of extreme compression followed by an expansion, potentially into a new baby universe. This concept doesn't just resolve the singularity problem, it opens up a dizzying array of possibilities for the origin and fate of our own universe. Could our Big Bang have been the result of a quantum bounce from a previous collapsed universe? Could the black holes in our own cosmos be the seeds of countless new universes, each with its own set of physical laws, its own stars and galaxies, its own potential for life? This isn't just a way to preserve information. It's a cosmic cycle of death and rebirth on scales almost impossible to comprehend. It paints a picture of a vast multiverse, constantly expanding and evolving through these cosmic birthing events. These theories force us to rethink the very nature of space and time. Inside a black hole, time and space swap roles, with time becoming a spatial dimension pointing towards the singularity, and space becoming a temporal dimension, inexorably pulling you forward. But if space-time is granular, as loop quantum gravity suggests, then our smooth, continuous perception of space and time is an approximation, valid only at macroscopic scales. At the Planck scale, time itself might not flow continuously, it might tick in discrete, indivisible units. Space might be woven from fundamental loops, like a cosmic tapestry rather than an empty void. This isn't just a technical detail, it's a fundamental shift in our understanding of the arena in which all of existence plays out. So where do we go from here? The observational breakthroughs of the last decade, the detection of gravitational wave by LIGO and Virgo, the stunning images of black hole shadows by the Event Horizon Telescope, have provided invaluable empirical anchors for our theoretical explorations. They have confirmed Einstein's general relativity in its most extreme domain, giving us confidence in the foundational physics, even as they highlight the need for something more. But these are just the first steps. The next generation of observational tools promises even deeper insights. Imagine the Laser Interferometer Space Antenna, LISA. a constellation of satellites in space, designed to detect gravitational waves from supermassive black hole mergers in the very early universe, with far greater sensitivity than ground-based detectors. While LIGO listens to the cosmic chirps of stellar mass black holes, LISA will tune into the low-frequency roars of supermassive giants, giving us a symphony of space-time ripples from across the cosmos. On Earth, projects like the Cosmic Explorer and the Einstein Telescope are planned next-generation gravitational wave observatories that will be many times more sensitive than LIGO, allowing us to peer further back in time and detect fainter, more distant events. These instruments could potentially pick up echoes from the quantum bounce or subtle signatures that distinguish between different quantum gravity models. The Event Horizon Telescope is also continually evolving, with plans for more telescopes, higher frequencies, and eventually space-based arrays that could provide even sharper movies of black hole accretion disks and event horizons. Imagine resolving the fine details of the photon ring, or even detecting the subtle distortions predicted by different theories of quantum gravity. These observations will be crucial for ruling out certain models and strengthening others, guiding our theoretical endeavours with real-world data. Beyond these direct observations, the future of black hole research will also rely heavily on theoretical advances and computational power. Quantum computing, for instance, might one day allow us to simulate the extreme conditions near a black hole's singularity, helping us test the predictions of string theory or loop quantum gravity in ways currently impossible. The mathematical frameworks themselves will continue to be refined, leading to new insights and potentially entirely new approaches to quantum gravity. There are also more speculative frontiers. Could we ever detect primordial black holes, tiny black holes formed in the early universe, whose evaporation via Hawking radiation might be observable? Could these mini black holes, if they exist, offer a window into the Planck scale, acting as natural laboratories for quantum gravity? What about the search for extra dimensions, a core prediction of many string theories? While current experiments haven't found them, the possibility remains a tantalizing avenue of research. Ultimately, the journey into the heart of a black hole is a journey into the heart of reality itself. It forces us to confront fundamental questions about existence, information, and the limits of knowledge. Is information truly conserved, or can it be irrevocably lost? Is our universe unique, or are we but one bubble in an infinite cosmic foam? Is space-time a fundamental entity, or does it emerge from something deeper, something quantum? Black holes are not merely astronomical curiosities, they are cosmic teachers. They are the ultimate proving grounds for our most ambitious theories. The places where physics breaks down not as a failure, but as an invitation to a deeper, more profound understanding. They remind us of the humility of science, that for all our progress, there is still so much we don't know, so many mysteries yet to unravel. But they also inspire immense wonder and excitement. The fact that we can even ask these questions, that we can formulate theories about phenomena so far beyond our direct experience, is a testament to the power of human intellect and curiosity. The quest to understand what happens inside a black hole is a quest to understand the universe at its most extreme, its most fundamental, and perhaps its most beautiful. It's a journey that continues to unfold, pushing the boundaries of human knowledge and redefining our place in an endlessly fascinating cosmos. And we, as curious explorers, are privileged to be on this journey, continually marvelling at the profound strangeness and elegance of it all. The black hole remains an enigma, but it is an enigma that tirelessly guides us toward the ultimate answers.